Hello friends, welcome to the next video in the Software Engineer to Applied Science Transition series. Today we are going to discuss about deep learning fundamentals. This is also a continuation of the last video where we discussed about machine learning fundamentals. I hope you guys went through the demo video and tried your hands on building linear regression models. As we discussed previously, deep learning is part or subset of machine learning which involves artificial neural networks. In this video, we are going to discuss what is feature engineering, why we should use deep learning, what is an artificial neuron, what are the different deep learning architectures, the pressing problems with those architectures, and what are the solutions to those problems. Suppose we are building an object recognition model, and this is one of our objects that we want to recognize through an image. And now the problem is, how do we pass this image to the model? One way to pass this image to the model is to pass the raw pixels of the image. So suppose the image is 100 cross 100, so the number of input features becomes 100 multiplied by 100 multiplied by 3. So 3 being the number of channels. So in total we have 30,000 input features. For a simple model like linear regression model or a decision tree model, predicting the object through this many number of input features will be very difficult. So another way to pass the image as an input to the model is to simplify the features. So how do we simplify the features? So for example, instead of passing the raw pixels, what we can do is we can pass the shape of the image and we can pass the color of the image. So we can say this is a round shaped object which is white in color. So now the model will be easily able to recognize that this is a ball. But this generally involves another computer program or a human to design these features, which can be very difficult and time consuming. Also, they do not always generalize or scale well for all type of problems. For structured and low dimensional data in the form of tables, it is easy to do feature engineering. For example, in our previous demo, we showed how to do BMI calculation using only 3 features: height, weight and age. But the world is not made up of tables. The world is made up of images. The world is made up of texts, sounds. So to make sense of this data and to build a model on top of this data, we need a complex model, a more powerful architecture. That's where deep learning comes into picture. Deep learning methods eliminate feature engineering by translating the data into compact intermediate representations. The lower layers of a neural network learn simple features, while the higher layers learn more and more complex features. For example, in this image recognition problem, the deep learning model tries to recognize the animal. The lower layers learn simple features like the edges, the simple edges. The higher layers progressively combine all those edges and form the outline of an animal. This results in simplification of the input from raw pixels to an outline and also improves the accuracy of the model. Another popular question that I encounter is why deep learning is so popular nowadays. So deep learning has been there since a long time, but recent developments have accelerated the adaptation and research in the deep learning field. The first reason is the compute. So more powerful machines with more RAM and different deep learning specialized hardwares like GPUs and TPUs have made it possible to train deep learning models in very short amount of time. Researchers now don't need to wait for months to train the model and see the results. The second reason is the availability of more and more data. Deep learning models are data hungry. They need more and more data to be trained. So with the invention of smartphones and other techniques like big data technology, it has been possible to gather this huge amount of data on which the deep learning models can be trained. The neuron in a deep neural network consists of input data, the corresponding weights to those data, an activation function and the output. The activation function is generally a non-linear function powering these deep models to build non-linear and complex mappings between input and outputs. Each artificial neuron is connected to other neurons via links that correspond to the axon, synapse and dendrite connections found in human brains. Each link is associated with a weight that determines the strength of one neuron's influence on another. Now let's discuss about different types of neural network architectures. The first one, this is called a multilayer perceptron. A multilayer perceptron is a class of neural network in which all the nodes or neurons in a layer are fully connected to all the nodes in the following layer. The next architecture that we are going to discuss is called a convolutional neural network, or in short a CNN. The CNN applies the same set of filters at different positions of the input data. This is very effective technique and is mostly applied in case of image processing. A CNN employs a mathematical operation called convolution in place of matrix multiplication in at least one of the layers. The convolution operation can be sometimes difficult to understand. I have posted the link to my blog where I have explained convolution more clearly. The next architecture that we are going to discuss is called recurrent neural network, or RNN. RNN is a type of artificial neural network where the output of last step is provided as an input to the next step. So temporal sequence data such as weather data, stock market data, or texts like sentences are good examples where RNN is pretty successful. Now let's discuss some of the issues associated with these deep networks. Let's talk about recurrent neural network. There is one problem with this architecture which severely impacts the model's ability to train longer sequences. The error signal used to train the network exponentially decreases the further you travel backwards. The problem is also called the vanishing gradient problem. Several variations of RNN are researched and used to solve this vanishing gradient problem. Some of the popular ones are GRU and LSTM. So GRU stands for gated recurrent unit and LSTM stands for long short-term memory. Both GRU and LSTM have several gates which enable RNN to memorize important information from the past. In mathematical terms, it optimizes the gradient flow mechanism. So it optimizes this gradient flow mechanism which eliminates the risk of vanishing gradient. Long short-term memory networks, usually called as LSTMs, are special kinds of RNNs. They are capable of learning long-term dependencies. They were introduced in 1997 and were refined and popularized by many people in following work. They work tremendously well on large variety of problems and were widely used for a long time until the invention of the transformer architecture in 2017. Now let's discuss another problem associated with deep neural networks. This is an example of a 34-layer CNN architecture. Deep models should be able to learn more complex representations if it has more layers. However, it was later discovered that after a certain number of layers, the deep models just stop learning and surprisingly sometimes degrade in performance. This paper from Microsoft Research in 2015 empirically proves that this architecture is showing poor performance after increasing the number of layers from 20 to 56. So how do we solve this problem? The same paper also provides a solution. The paper introduces a new network called the residual network, or in short Resnet, which employs shortcut connections. In this network, the input is added back to the convolution output after few layers. The paper mentions that in some cases an identity function might be what the model needs, which is very difficult to formulate because of the presence of these non-linear layers. A skip connection allows the model to drive the non-linear layer weights to 0 and achieve an identity mapping. So if the model wants to achieve a function called y equal to x, now this residual connection will enable the model to do that. After adding these shortcut connections, the model with more layers performed better than the model with less number of layers. I have pasted a link to the Resnet paper in the comment section below. I would recommend going through the paper, and if you guys have any doubt, you can ask in the comment section. For this week's study material, I would recommend course 4 and 5 of Deep Learning Specialization in Coursera. You should also follow the links and papers that I mentioned in the video description. These videos are essential to build a strong theoretical foundation on deep learning. In future videos, I will share more study materials which will help you build these deep models yourself. In the linear regression demo video, we were calculating gradients by hand and used gradient descent to train the model. This is no longer feasible in deep models because deep models can be very complex and calculating gradients by hand and back propagating can be very difficult. So to solve that problems, applied scientists now have come to a stage where they will have to learn a framework, a deep learning framework. TensorFlow and PyTorch are very good deep learning frameworks which will help you build these deep models. We are going to discuss more about these frameworks in our next video. I hope you found this video useful. Please do not forget to like and comment this video and subscribe to the channel. Also share this video with as many people as possible. This will motivate me to build more such videos faster in future. So that's it for today. I will see you guys in the next one. Thank you.